Everyone, welcome back to the Linux. Today we are going to see about support vector machine. The support vector machine is a supervised machine learning used for both classification and regression tasks. The main goal in the SVM is to find the best optimal hyperplane to separate the both classes. For example, let's draw the graph, and these are the region of in a class 1, and these are the region of in a class 2, and it will find the best optimal plane to separate the both classes. We can we can place the hyperplane here also, but we can place the hyperplane here also, but we need to find the best hyperplane so we can separate the both classes. Key concepts. The hyperplane is used to separate the classes, so we can when the new data is come based on the hyperplane, it will separate the data into in a classes. For example, let's draw in a graph. These are the class 1, these are the class 2s. For this data, we need to draw some hyperplanes to separate these classes, because this is in a class 1, this is a class 2. So we draw a hyperplane to separate these classes. The support vector. The support vector is the data point which is near to a hyperplane. This is an hyperplane. The support vector is near to a hyperplane. For these are the support vectors because it's near to the hyperplanes. These are also in a support vectors because it's near to a hyperplane. The distance between the support vectors and to the hyperplane is called as margin. In this case, this length is margin. Here it is, this length is margin. In SVM, it will maximize the distance between the margin, so we can predict the classes, so we can classify the classes accordingly. For, for example, this is a margin for a class yellow, and this is the margin for a class blue. This is a margin distance. In a SVM, it will find the best hyperplane, so it's usually maximize the margin, and so we can when the new data is comes, and it will classify the data points accordingly. And there are two types of margin: hard margins and soft margins. The hard margins, some data points cannot allowed in the other classes. For example, these are the blue classes, these are the yellow class, and if any data which is near to in a blue classes, it will in the odd margin, it will must be in a similar classes. For example, in this case, it will find the hyperplane like this. It always find the hyperplane in a straight line, so these no data points cannot allowed in the other classes. The data points below the line which is strictly in a class 1, the data points which is above the hyperplanes which are strictly in the class 2 in class 2. But in the soft margin, it allows some data points into any other classes. For example, if some data points are in the class blue classes and some data points are in the yellow classes, and it will allow some data points into any other classes by introducing a slack variable. We introduce the slack variable to the all the data points. We can assign the value to any slack variables. For example, it's in a margin for in a blue class. This is in a margin for in a yellow class. This is in a hyperplane. In this soft margin, it allows the some data points in the other classes, and it will introduce this slack variable if some data points will place inside the margin. The slack variables are near to or in the range of 0 to 1. If some data points are misclassed, for example, the blue class are placed in the yellow class, so then the slack variables are above the 1. If the class are correctly placed, if the data points are correctly placed in the class, so then the slack variable is 0. During the soft margin, we will use the in clause to assign the value to NA, assign the slack value to NA data points. And the kernel function will used for in a long when the data is not separable by a linearly. So the kernel function will transfer the data points into an higher dimension. So in the higher dimension, we can separate the data linearly. How does it works? In in SVM, for better understanding, I will draw the graph. Usually we trained in the label data set, right? So let's draw the class 1 data points. And these are the class 2 data points. Here it is, we can linearly separate the classes. So if I draw the hyperplane, this is an hyperplane. This is in a margin line for an a class 2, and this is in a margin line for an a class red. The distance here it is hyperplane, and this is margin line. The distance between the hyperplane to this support vector, it's called a margin. This is margin line. This is margin distance. In SVM, usually we need to maximize this margin line. We usually maximize this margin line so that we can separate the classes efficiently. For example, if I draw the hyperplane like this, whenever some blue data points comes here, it will consider as in a red classes. So it's not in a good classification. So if I draw the hyperplane like this, whenever the red class data points occurs here, and it will consider as in a blue class. So it's not also in a good hyperplane. So we need to place the hyperplane correctly. So whenever the new data will comes, it need to in a classified perfectly. For example, if I draw the hyperplane like this. Here we can see that the both distance are equal. See, so it has a maximum probability. So the both data can classify its classes efficiently. Here we are seeing in a linearly separable data, right? What if the some classes are not linearly separable? For example, if I see these are the class ones, these are the class twos. Here we can see that there is no linear relationship between the red and blue. So we cannot draw the straight line like this because we cannot classify these things to this class. So in this case, we use some function called kernel function. So that the kernel function transfer these data into an higher dimension, into an higher dimension. So in the higher dimension, we can linearly separate these classes. For example, for picture, for example, this is an array. Let's take this is an input. If I plot the graph, it looks like this. The red classes are here, and greens are reds are surrounded by a class green. You can see that here. So here it is a data is not linearly separable, right? The red classes and the green classes are not linearly separable. So we use the kernel function to transfer this data. Here it is in a two dimension, right? So we use the kernel function to transfer this data into a higher dimensions. So we can linearly separate these classes. Here we can see that the green classes are settled in the down in higher dimensions, and the red classes are settled in the upper in the higher dimensions. So in this case, we can linearly separate these classes, these blue and red classes, by this hyperplane. But the hyperplane, sorry, the kernel function not explicitly transfer the data or transfer the data points into a higher dimension. And it's like it doesn't transfer the data points in the vectors in coordinations in the hyperplane. It simply find the scalar values of in a hyperplane in the higher, sorry, scalar values of in a data points in the higher dimensions. Here we can see that it's mapped the data into a higher dimensional features in this space pi of x, and it will compute only the inner products via of in a kernel functions, and it doesn't explicitly find the pi of x. It's avoid some computational costs, computation efficiency to entirely transfer the data into an higher dimension. It's like when you transfer the entire data into an higher dimension, you need to find the coordinations and vectors, and also in a directions of in a each inputs. Like if the number of inputs are 4, number of inputs are 3, you need to find the 3 vectors and its directions, like unit directions. There are so many things. So it doesn't calculate these things. It will simply calculate the scalar values in the higher dimension. That is enough to linearly separate the data using in a hyperplane. These are the common kernel functions for a linear kernels, like the dimension are 1 or 2. We use in a linear kernel function. For a polynomial kernels, when the inputs or features are in the more than the two dimensions, use this kernel function, and based on the kernel functions, we select the based on the data points, we use to select the kernel functions. The choosing in a kernel function for in a problem play in a vital roles. So we must select the kernel functions accordingly. Advantages. It will effect you in a higher dimension space and robust to overfitting. And there is also a disadvantages. It has in a computational intensive for in a large data sets, and choosing a kernel functions, it's more complicated and less effective if the number of users is much greater than the number of samples. Applications. We used to classify the text for like spam detections and sentimental analysis in the movies, and image recognitions and image classifications, and also financial forecastings and handwriting recognition. In summary, the SVM find the optimal hyperplane to classify the data with a maximum margin, and soft margin allows handling a non-separable data within a slack variable. The kernel tricks enable the non-linear classification by mapping into a higher dimension space, and it's widely used in the various domain due to its effectiveness. And that's it about the SVM in the supervised machine learning, and it's also used in the both regression and classification tasks. Thank you. Let's see you on the next video.